Turn the microphone on.
Let's turn it back on. Okay. All right. So, good afternoon, everyone. We've got a great group of people here with us in person and a number of people online. Those of you online, when you would like to ask a question or say something, please let us know. Raise your hand, say something in the chat, and we will give you permission to speak, okay? Oh, we're so glad to have all of you with us here today for the VIRTEX Symposium here today on December the 8th. We're talking from Johns Hopkins University's Applied Physics Laboratory. We've got some wonderful scientists and kids from the Boys and Girls Club of Allentown. Woo! So let's go ahead and let you know what to expect for this next hour. We've got our agenda. The first group that's going to be talking is the Boys and Girls Club of Allentown. And then after that, we are going to be hearing from 4 scientists about their careers and their research. Each of them is going to get to talk for about 5 minutes. If you have questions during their presentation, raise your hand, and as soon as their presentation is over, we'll take time for questions, okay? For those of us in the room, we're going to use the microphones in the room. For those of you online, you are welcome to talk. We'll just have to unmute you when it's time. And again, if you prefer to enter questions in the chat, you can do that as well. So let's go ahead and let's get started. Why don't we go ahead and prepare for the Boys and Girls Club to get ready to come on up.
Good afternoon, everyone. Can you hear me? My name is Molly Lick, and I am one of the education directors for the Boys and Girls Club of Allentown. Thank you. On behalf of all of the 5,000 Boys and Girls Clubs all over the world, I would like to extend our sincere thanks to the people at NASA's VIRTEX for offering this amazing educational experience for our club kids. The curriculum and lesson plans you provided were fun, interesting, and easy to follow. Today, the kids would like to share with you some of their favorite activities from their VIRTEX experience. First up, we have Isabella, Ryan, and Jaden, and they will talk about crater creations.
A crater is a circular hole made when a meteorite impacts a surface.
We created craters in a bin filled with sand, flour, and hot chocolate mix.
Here we see the various parts of a crater like the floor, walls, and the ejecta that is thrown out of the crater on impact.
Is that it? Thank you so much, guys. Thank you. Thank you. Next, we have Damien, Anna, and Marley, who will tell you all about edible rocks. Come on, I come in a little closer. Here we go. Perfect. Who wants to hold the microphone? You got it? Thank you.
A meteor is a piece of rock from space that reaches the planet's surface.
Some candy bars look like meteorites.
For instance, Nestle Crunch looks like Klondike. Almond Joys look like a fusion crust that forms when the outside of the rocks melts. Three Musketeers have lots of holes, just like vesicles in some meteorites.
This experiment was fun and delicious.
Thank you, NASA, for coming up with such a fun activity.
Thank you, guys. Very well done. Good job. Thank you. Next up, we have Jeremiah and Annabelle. and they will show you our homemade nebulas. There you go, honey.
Nebulas are clouds of dust and gas formed by dying stars, and they help make new stars, planets, and life.
We created these nebulas using shaving cream, glue, and red, blue, and green food coloring.
This is one of our favorite activities because it was messy and fun.
Thank you, NASA, for coming up with such a cool activity.
Thank you. Thank you very much. Part of the NASA VIRTEX program is to pair us up with a NASA scientist as a mentor. The point of this is to make science accessible and attainable by letting them get to know scientists as real people. We were very fortunate to have several virtual meetings with planetary geologist Dr. Kirby Runyon. Brooke and Leo have a few words they'd like to share about Dr. Runyon. And Dr. Runyon, I hope you're watching.
Dr. Runyon was our NASA mentor.
We learned about zero gravity flights from him.
Dr. Runyon's favorite planet is the moon.
He answered all our questions and was also funny and smart.
He showed us that careers in science are possible.
Thank you. Thank you. Thank you. I need the microphone back. Kids, you want to come and join me up here real quick while we say one last thank you? I want to say thank you
Let me go ahead
again.
and say that Dr. Runyon is on and he's sharing his camera, just to let you know.
Okay.
Hey there, super proud of you guys. Wish I could be with you today.
Oh, we miss you.
Thanks, miss you too.
Did you see the picture we did of you?
I sure did.
It's beautiful, right? I love
Thank
it. So I want to thank you again to our hosts here at the APL. We had a great day, and we look forward to enjoying the rest of the symposium. So thank you very much, everyone. Thank you. Good job, guys.
Bye. Bye, everybody. Bye.
So we have another club that's on its way that's going to be watching in person. So they're just stuck in traffic, but they'll be here in about 8 more minutes. And so I believe next we were going to have Dr. Lene Quick Henderson give a presentation, if she would like to come on down. And I have a slide that I can share, but it's easier not to right now. So we'll just let her share her slides instead. Part of what we're doing today is we're giving everybody the chance to meet and ask questions of some amazing scientists and technicians and NASA staff to hear more about their careers and what they do. And we've got a slide that's coming up right now.
Good afternoon. It's wonderful to be here with you all and to see your faces and the very cool work that you've been doing, and to see Kayla. Hi. And so I'm Dr. Lene Quick Henderson. I am a planetary scientist here at the Johns Hopkins Applied Physics Lab. And so I'm just going to tell you a little bit about myself and about the work that I do. I'll start out with telling you about myself. I'm originally from Greensboro, North Carolina, so just a few states down south. When I was your age, I was not thinking about becoming a scientist at all. I was more into English and creative writing and language arts and all of those things. So you all are already years ahead of where I was at your age. However, by the time I got to high school, I had very good biology, earth science, and physics teachers that interested me in science, and they encouraged me that I could become a scientist. But just so you know, I was a regular kid. I played dolls with my sister all the time. That was mostly what I did as a kid. I also, when I was in high school, I played the saxophone. The picture up top of is me and my husband Lamar, and on the bottom is our dog Raven. She's a border collie, Aussie Shepherd mix, and we love her very much. And since you all talked about Dr. Runyon, if you look 1, 2, 3, 4, 5 people over, that's Dr. Runyon. We went to graduate school together, and so we became doctors at the same institution at Johns Hopkins. So I was excited to see the picture of him and hear his voice. Hi, Dr. Runyon. And so I didn't really think about college, science until I got to college. I went to college at North Carolina A&T State University. And by the time I got there, I wanted to be an astronomer, and I was pretty good at math. So I majored in physics, and I spent my summers doing science. One summer, we went to A&T's farm, but we stayed far away from the animals, and we took very heavy instruments and hit the ground, and we simulated earthquakes. That was something we did. I also spent a summer at an observatory in Charlottesville, Virginia, studying brown dwarfs. Brown dwarfs are stars, or they're not stars, but they are objects that really want to become stars. They're too small to become stars. They can't fuse hydrogen into helium. And then I spent a summer at NASA's Goddard Space Flight Center studying Mars. And what was so exciting about Mars was we think, as many of you probably already know, we think that long ago, Mars may have been more similar to Earth. It may have had seas, it may have had oceans. And what allows Earth to have seas and oceans is that we have this nice global magnetic field. We think that a long time ago, Mars had one too, but now Mars's magnetic field is very patchy. It's in its surface rocks, and that's why it looks like it does today and doesn't look like Earth. And so then I went to graduate school, getting closer on this timeline to meeting Dr. Runyon. But that's when I first started studying planets and moons. And this was the type of thing that I would study. We see this image here. And so this is a telescopic image of another star named Beta Pictoris. And these little kind of I don't want to say lines, but what looks like light shooting from the sides of it, that is a debris disk. And so that's where planets form. So it's a baby star, and planets are going to form from the dust and the gas that's in this disk. There's already one planet called Beta Pictoris b. It's about 10 times bigger than the planet Jupiter. And Beta Pictoris as a star is very interesting. It's almost twice as big as the sun. It's trillions of miles away. It's 9 times brighter than the sun. It's hotter than the sun. And the one planet, Beta Pictoris b, that we see orbiting it, a day is only 8 hours. It orbits very fast. And it's about 10 times bigger than Jupiter. And so what I study now is mostly moons, where the outsides of these moons are made of ice, but they have oceans on the inside. This is Jupiter's moon Europa. This is my very favorite moon to study. It's about the same size as our moon, but it has a lot of ice and water. And then beside it, we can see here's a close-up image of this area. This is a region called Connemara Chaos, and they are just large icebergs. Some of them are as big as mountains, and they float around. Because Europa has a lot of water, and we know that life needs water, we're excited to study Europa, and we're sending a spacecraft to determine if there are places inside of its ice and inside of its ocean, which we can't see because it's again on the underside of the ice, that could be habitable, that could be hospitable to life. So could there be habitats there where life could be? And so we were very excited to have our Europa Clipper spacecraft, and we're sending it to Europa to help us answer these questions. On the top left here, it's being being ready for launch. On the top right, it's in this top part right here. I don't know if you can see my arrow, but that's this whole thing here. Here's the spacecraft, And here it is at the top of the rocket. It launched last October. And this image at the bottom is how it's going to look once it unfolds. It gets to Europa and it takes pretty pictures and it gets data and it helps tell us about the ocean beneath the ice and about the surface geology. And so we study Europa the way that we would study other planets. Instead of studying rock, though, we consider ice and things like that. So that is the end of my presentation. Thank you all for listening. Are there questions?
Thank you. So for those of you online, if you have a question for Dr. Lene, please go ahead and either raise your hand or enter it in the chat. If you raise your hand, we'll unmute you. For those of you in the room, think about what questions you may have, and we'll have you come down and talk into a microphone so everybody online can hear you. We've got some kids with questions, so have them come on down to a microphone.
My name is Ryan, and when is the Europa Clipper gonna land on Europa?
That's a wonderful question. It will get to Europa in April of 2030. So it takes a while to get there. It's going all the way out to the outer solar system to Jupiter. And so that's why it's so important that you all are studying science now, because some of us who are studying Europa, by the time the spacecraft gets there and starts taking data and sending it back, we won't be so young anymore, or young-ish. And so we need you to come take our places. Good question. You're welcome.
My name is Brooke,
Hi, Brooke.
and my question is, so like, were you guys how did you meet Dr. Kirby Runyon?
How did I meet Dr. Kirby Runyon? I will tell you, Brooke, that is a fantastic question. So when I was getting my PhD, my doctorate degree to become a scientist, I had an office right upstairs, and Dr. Runyon came to the same school I was attending, came to Johns Hopkins, and he was doing planetary science research just like I was, and we ended up sharing offices, and we shared an office, and that's how we met. Yep.
Thank you for answering my question.
You're so welcome.
Hi, my name is Isabella, and I'm wondering, how do you know when they're going to get there? Like, how do you figure out when they're going to get there?
When the spacecraft is going to get there. Rocket scientists figure that out. They use lots of math, they use lots of equations, and that's why it's important to pay attention in math class and love math, as I'm sure that many of you do, because what you can do is you can calculate what it will take for a spacecraft to get to a planet or a moon. I'm not sure how many of you saw or have seen Hidden Figures, and Katherine Johnson did that. And so now people do something very similar, but they're using, computers and software and all of those things.
Thank you.
You're welcome. Thank you.
My name is Annabelle, and do you know how much time it takes for a rocket ship to get to Europa?
It takes about 5.5 years. Yeah. Again, that's why we need you all to keep studying science and one day take my job. That's right.
Thank you.
You're welcome.
Hi, my name's Jaden LeBron. So, when was this rocket made?
So, when was the rocket made? That is a good question that I don't think I know the answer to. It did launch last year. I'm not sure when it was made. I'm sorry, I can't answer that question. Does anybody, Kayla, do you know? Okay, I can't, I don't know. I don't know when the rocket was made. You've stumped me.
Thank you for answering my question.
My name is Damien, and when did you like science?
When did I like science? I started liking science when I was in 9th grade in high school. I had a very good biology teacher named Mr. Surgeon, and his daughter was actually one of my classmates, and he really made biology fun and made me see that science could be fun in a way that I didn't think about before then.
Thank you.
You're welcome.
Hey, my name is Marley, and I have a question. How long does it take to make a spaceship?
How long does it take to make a spaceship? Well, let's see. So we have this Europa Clipper spacecraft that we've been talking about. We started making it in 2014. So, and then it launched last year. So it took about 10 years for this specific spacecraft to be made, and all the instruments that went on it. So it takes a while. It takes a while. It took about 10 years. And so some of you may have been babies or may not even have have graced us with your presence when it was being made. Yes, ma'am.
Did you say 2014?
2014. And so it took about 10 years.
That's my birthday year.
You oh my gosh.
I was born in that year.
Your birthday, oh my goodness. You are a Europa Clipper baby. Yes, you are. Okay.
All right, let's go ahead and let's thank our speaker. Do you have any final things to say or share?
Just keep doing science. I look at your faces and you all make me happy that I'm a scientist, so I can come talk to you, and maybe one day you'll be where I am, talking to folks that were born the same year your spacecraft was built, and encouraging them to become scientists. And so we need you in science. Keep, as you're learning science, keep making sure you're doing your reading and your writing and your math. And we're all very proud of you and happy to be able to talk to you all.
I have one follow-up question.
Sure.
You say it takes about 10 years to build one of these.
It took about 10 years to build this one.
To build this particular one. So my question is, how do you keep up with the technology? Because I'm sure the technology in that 10-year time span varies greatly. So how do you keep up with the technology in that 10-year process?
Sure. So I'll give an answer, and I will ask Dr. Alexandra or Dr. Ed to correct me if I'm wrong. So a lot of times the instruments that go on these spacecraft are what we call heritage instruments. So they're new instruments, but they're built kind of, I don't want to say that they're copies, but they're very similar to instruments that have operated on other spacecraft that we know can operate well in space. And so that's one way that we keep up with the technology, or that's one way that we kind of, keep constant and keep consistent with the changing technology. I don't know if you all have other ideas of. Okay. All right. Okay. Thank you.
Next is Kayla. All right. So I'll introduce. All right. Next we have Kayla Berry. And let's see, where's your presentation?
Christine, Christine's pulling it up. I could just go without it. That works.
Well, we want to be able to see where she goes.
I could pull up a shortcut too.
Yes, if you go get your laptop and we can plug it in. Okay, Kayla Berry is visiting us from Goddard, and she is going to bring her laptop up here to do the presentation from her laptop. So just wait a few minutes. Yes, thank you. Thank you for your patience. All right, wasn't that a cool presentation from Dr. Lene? Really inspiring, right? We love working with her here. She's awesome. Yep. So I want to also, someone asked about how long it takes to build a rocket. So that's the vehicle that we use to launch the spacecraft into space. So the spacecraft is taking a ride on the rocket. So it took the rocket 10 years, I think we decided to, or I'm sorry, it took the spacecraft 10 years to be built. But the rocket, we don't make rockets here. The rocket we buy from people who make the rockets. So I'm not sure how long it took to make that particular rocket, but that would be, yeah, a cool thing to look up. So who's making our rockets right now? What? Northrop Grumman, do they make rockets? I know SpaceX makes rockets, yeah. Boeing? Yeah, okay. All right, so are we ready? Oh, she's got to bring it up. Okay, awesome.
So our next speaker is Kayla Berry. She works for NASA Goddard Space Flight Center, and we're delighted to have her here. And let me go ahead and tell it to go into slide mode. It's covered by my other controls. Hold on, I'm just about there.
Thanks, Dr. Alex, for teaching us about rockets, and Dr. Lene for the presentation. And congratulations, you all. I understand you accomplished some exciting things to be here today. Yes. I love getting to hear a little bit about what you were working on. So I'm Kayla. I work just up the road at NASA Goddard. Thanks, Hopkins colleagues, for having me come and join you today. And thanks for having me come and join you, Allentown Boys and Girls Club. My job is a mixed up job. I have a confession. I'm not a professional scientist. I'm not Dr. Kayla. I'm just Kayla. But I get to work with a lot of scientists who ask really, really exciting questions about how our planet works and what our place is in the solar system and the universe. And I get to work on helping to enable that science out in the field here on Earth and helping to tell the stories of that science. It's really important that NASA belongs to all of us, right? NASA is all of ours, and you all have a right to know what NASA is up to. You have a right to access information about the science that's happening inside of the agency. So part of my job is to work on making information more available about what's going on at NASA. The first few pictures here are of me doing field work. I love doing field work. It's the best part of my job. Sometimes Dr. Alex and I get to go on field expeditions together. We'll be out in the middle of nowhere. We'll be learning about planet Earth. Most of the time, though, this is truly not what my job looks like. More often, I'm sitting at that laptop at a desk in an office. If we go to the next slides. Thanks for the slide help. I get to take back stories from fieldwork and work on sharing them on social media and on the web. So this is an example from a couple years ago. Right now I'm one of the managing editors for the NASA Solar System social media accounts. Next slide, please. You'll recognize a familiar face. Oh, so sorry, Christine, I didn't even look over to see if you were just there at the keyboard. So a familiar face on this slide. At this field site, we were at the location of a supervolcano that blasted like an unimaginable amount of ash way, way, way up into the air long, long ago, dropped all the ash down on the ground, and Dr. Alex and the other scientists can tell you a lot more about why that's amazing, but I got to be out there and help to kind of ask questions and share that information online. Next slide, please. I also write for NASA websites, telling the big picture story of how we use Earth as a test lab for other worlds. So one way that we can learn about other planets in our solar system and beyond our solar system is, it's like a little party over here. Yeah. I like it. One way we can learn about what's out there is by sending robotic explorers, right? We can send spacecraft like Europa Clipper to explore other worlds and sometimes even touch and land on other worlds. Another way we can understand how planets work is by studying the one that we are all sitting on right now. We live on a planet, right? Earth is the planet in our backyard. And Earth has examples of landforms that are common throughout our solar system. Like, okay, real quick, everybody raise your hand for me. Everybody raise your hand for me. Okay, keep your hand up if you are used to thinking about volcanoes on Earth. We think about volcanoes on Earth. We've heard about volcanoes on Earth. Okay, keep your hand up if you know of a volcano on another world beyond Earth. Oh, we got a lot of hands up. Anybody want to shout out a world they're thinking of where they imagine a volcano might be? Shout it out, shout it out. You're okay. Venus, lots of volcanoes on Venus. Yeah, anybody else want to add to the list? Mars. Yeah. Anybody else? Okay. Venus, that's great. Mars, that's great. The moon has a volcanic past. Volcanoes are super common throughout our solar system, and there are a lot of landforms like this. Like we can see erosion patterns on other worlds. We see even kinds of ice on other worlds. We see craters on other worlds. And if we want to get like human eyes and brains up close to those things, planet Earth is a really good place to do it. So that's kind of the big picture story that I get to help tell. Next slide, please. The other piece of my work right now is communication around lunar science. So this is a picture of the Daily Moon Guide. You can visit this. It will let you play around with like moon phase for every day of the year. So if you want to know what the moon phase would be for your birthday, or like when the special events are happening on the moon in the coming year, we're going to release the new one based on the 2026 data in the next couple of weeks. And it'll give you like recommendations for stuff to look at. So this is a fun thing that I love to get to work on. Next slide, please. And it's out there for you all to play with and tinker with. I get to work on NASA's Moon website, where we just tell stories about fundamental lunar science that anybody might be interested in looking up. And next slide, please. I get to work on a program called International Observe the Moon Night, which you are all invited to join in if you would like. This year it's on September 19th, or excuse me, next year it will be on September 19th. And if you choose to observe the moon around that time, you will be doing so with people all over the world. The last few years, about 1 million people observed the moon together. This past year, it was about 1 million people in 128 countries. And people do this in all different ways, like by making moon art and music and poetry and learning about science and doing science and getting familiar with exploration and technology and taking on challenges in those areas. So you're invited. I wanted to let you know. Next slide, please. Oh, there's the QR to the program webpage. And before I wrap up, I'll let you know about one more thing that you are all invited to participate in that's coming up this week. This Wednesday afternoon, I'm going to be in the multimedia studio up at NASA Goddard, and we're going to be doing an episode of a show called NASA Science Live. And the point of NASA Science Live is to have scientists come on air and just like share about their work, and people will be writing in on social media and on the YouTube stream using hashtag #AskNASA to ask questions, and they'll be answering questions on air. So if you go to the next slide, that QR code will take you to the YouTube channel. It's on Wednesday at 3, and if you're available and interested, everyone's invited to join in that as well. So that's a little bit about me and what I'm working on right now. Before this, I've had like a lot of different kinds of jobs. I have a mixed up job now, but these are some of the things that I get to work on, and I'm really glad to have a chance to share with you and invite you into today. So happy to take any questions. So thanks again for having me.
Okay, for those of you online, again, if you enter a question in the chat, or if you want to raise your hand, we'll unmute you so you can ask your questions. Those of you in the room, if you have questions for Kayla, please come on up. We'll use a microphone. You can come up one at a time. And that's for both clubs, now that we've got both clubs here. Anybody who has a question for Kayla about what she's done, about her career, about NASA, come on forward to the microphone. And come on forward to the microphone.
My name is Brooke Bartholomew. I have a question about, is there any other planet, like the regular, like mostly the, like people say planet. I mean, like if you say the sun and then if you say to the sun or to Pluto's, like those planets, is there, is there any other volcanoes like similar to the planet names?
Volcanoes similar to the planet names? I need help understanding your question. Will you ask me again?
I mean, like planets that kind of have the same name, but have different stuff instead of the volcanoes on the.
Like planets that have different kinds of geology and landscapes other than volcanoes? Ooh, so the ocean worlds in our outer solar system are examples of really exciting places that don't have the kind of like rocky volcanoes we see on Earth. Just like Europa, the moon that you were hearing about from Dr. Linné, that world is like an ice shell with the ocean under the ice shell and then like more stuff under the ocean. So there are a few worlds that are kind of like that. Anybody else want to add on any other types of worlds? We got gas giants in the outer solar system, worlds where you like, okay, I want you to imagine you are a spacecraft. You're coming in for landing. There's a huge planet below you. You approach the surface, but you never land. You just sink in. You sink in, and it's like clouds rising up around you. That's what we might imagine happening on like a gas world in the outer solar system. Yeah, all kinds of different worlds out there. And then there are like literally thousands of planets outside of our solar system, which nobody even knew about a few decades ago, but now we're starting to learn about them. So tons of different kinds of worlds.
Thank you for answering my question.
Sure.
How long have you worked on your job?
About 5 years. Most of what I do, I learned to do while I worked here. Like I brought skills from other jobs, but if y'all are like curious people who like to tell a good story, we need all kinds of people doing all kinds of work at NASA and in the science world.
Hi, my name is Isabella, and I'm wondering why did you choose your job that you're doing right now?
Oh my gosh. Well, okay, so something I feel really strongly about is that science practices are really just human behaviors. So like not all of us go through the intense process of becoming a doctor, right? And becoming a professional scientist and doing that kind of rigorous all day, everyday work. But all of us ask questions in our lives and like take in information about the world around us. We make observations. We like make connections about what we're seeing. We do the best we can with the information we have. And then sometimes we fail and we get new questions because we didn't have all the information in the first place, right? Like science is for everyone. Science is human stuff. And something I love about working at NASA is that the stuff that we make is for everyone in a different way. Like it's all free, it's on the internet, which is how it should be. It belongs to everybody. So I'm a science is for everyone person, and getting to make things that are available for free is one way I can try to live up to that in the world.
Thank you.
Sure.
We have a question from online from the Boys and Girls Club of Hudson County. How did you get into doing field research?
Oh my gosh, I got really lucky. I applied for this job. I never would have imagined that this job existed. I didn't know this was a thing. But I used to do outdoor work, and I had some experience with like emergency planning and planning big complicated trips for lots of people and like deciding what to do when a wildfire is coming really fast and stuff like that. And then I learned about this job, and I learned that that I could apply that kind of experience in a totally different world where people are going out and studying Earth to understand our solar system and our universe. And I was like, yes, please. I would love to try that. So I got really lucky.
Why do you like working out in the fields?
For me, being outside is a really good experience. Anybody else here just like to like look at trees moving in the wind or like get outside and get under the sky a little bit? Yeah, I mean, field work, I gotta be honest with you, it's hard work. We work really long days. We go hard when we're doing field work. And it's amazing to just get to be up close and personal with this planet in that way. It's a really special thing to get to do.
Thank you.
Sure.
So, what inspired you to work with NASA?
Oh gosh, I did not think I was gonna get to work with NASA. I applied to like a lot of other jobs when I was looking for a job around the time that I got to start doing the job I do now. But I was excited about getting to be part of something big and getting to work on stuff that's just available to all of us. And so I put my name out there, and here I am. It worked out.
Thank you.
Sure.
We've got one more question online about the volcanoes on Mars. Are they still active is the question.
Oh my gosh, are you our next speaker?
Our next speaker can talk a little bit about
an
that.
expert on Mars volcanoes, so
Okay.
I'll leave that one to Dr. Alex.
Thank you. Thank you so much, Kayla.
All right, awesome. So now I just need to figure out how to share my slides and make sure I can do it without messing everything up. So Zoom, share, and then I'm going to go into slideshow mode, and let's see. There we go. All right, awesome. So, all right, so yes, I am a planetary volcanologist here at Johns Hopkins Applied Physics Lab. And as Kayla was just mentioning about studying planetary processes on Earth and then looking at those similar processes on other planets, that's where I started. I started learning about geology and volcanoes right here on Earth. I went to UCLA and I got my bachelor's of science there, and then I did an internship at the Hawaiian Volcano Observatory. I was actually rejected from 4 grad schools that I applied to, but I got into my 5th one. So that just goes, to tell you, don't ever give up. Even if you get rejected, just keep going, keep trying, and eventually you will get in there. So I ended up getting accepted to Michigan Tech, where I got my master's and my PhD, studying really large volcanic eruptions that they eject really large ash clouds into the atmosphere. And now I'm looking at similar types of volcanic processes on other planets. And I do also want to note my second bullet there. I did struggle with math and physics and chemistry, but I wasn't going to be a mathematician or a physicist or a chemist. I wanted to be a geologist. So I knew I just have to get good enough grades to be able to be good at geology. So even if you're not getting straight A's in those subjects, unless you want to be a physicist, don't worry about not being the best at physics. You just need to know enough to be able to apply it to your other sciences. So that's just throwing that out there because I did struggle a little bit. So geology, what is geology? It's the study of Earth. It's the study of physical parts of the Earth. And we can apply this to rocky planets, other rocky planets as well. And that's what we call planetary geology. And so Earth geologists, we study rocks and minerals, we work out in the field, we study how Earth changes over time. Planetary geologists do basically the same thing, but we can't actually be physically on that planet to study it. So we use a lot of spacecraft imagery and satellite imagery that we were showing you today. But as Kayla mentioned, we also do a lot of analog studies that the more we can understand a geologic process here on Earth, we can maybe understand it a little bit better on another planet as well. So here's a picture of what Earth geologists look like. If you take a class in geology in college, for example, a lot of your classes will be outside. That's the fun part. That's what appealed to me. I loved being outside. I'm definitely a nature person. So when I saw a major that would take me outside studying the natural earth, I thought, well, this is great. This is definitely something that's right up my alley. So that's some of the pictures from there. And then on planetary geologists, again, the only type of field geology that we've done any place other than Earth is the Apollo astronauts on the moon. So they were up there, they were doing geology, they were collecting rock samples, and they brought them back to Earth. But otherwise, we really do have to depend on rovers or other spacecraft imagery. And then again, there's the analog science. So we do a lot, we study, this is here in the Valley of 10,000 Smokes in Alaska, where we're looking at this huge ash deposit, trying to better understand it and compare it to what we see on Mars. And so this is just really quick to understand our solar system, but what I really wanted to show you was the rocky planets that I study are in the inner part of the solar system. So the outer part of the solar system with the gas giants and everything, I don't know as much about those planets because they don't have rocks on them. So I'm really focused on the inner part of the solar system. And just a fun little picture to show you for scale. You all did the distance today between all the planets, but this is what they look like for like their sizes compared to each other. And you can see little bitty Earth right there. It's just like a tiny little speck of dust almost in our solar system. Our Earth is really small, but it's still a really cool planet. And here are the other rocky planets. Earth and Venus are very similar in size. Mercury and Mars are much smaller. All right, so volcanoes. So again, I study volcanoes, and the biggest volcano in the solar system is Olympus Mons. So it's the one that's like all the way on the right side of the slide that you're looking at. So it's much bigger than the biggest volcanoes on the biggest volcano on Earth is Mauna Kea. And it's much bigger than that. And then we also have volcanoes on Ceres, and then Venus has a lot of big volcanoes as well. But Olympus Mons is the one that rules them all. That one's on Mars. So let's see. Mars, volcanism is a fundamental process on Mars. Mars at one point was very volcanically active. It is not active. Volcanoes are not active on Mars at this point, as far as we can tell. But, you know, maybe if we went there and we could study it more closely, we might find something different. But at least as far as we can tell right now, it's not active. And then I have the picture of the Hawaiian Islands underneath there to show the comparison between Olympus Mons, that's the volcano on top, and the entire Hawaiian island chain. So if Olympus Mons was on Earth, it would be the entire Hawaiian island chain instead of the biggest volcano, which is just a little bit piece of that, the big island there. All right, and then another process that's really dominant on Mars is sedimentary geology too. So here we found in Jezero crater a little ancient river delta, and I'll get a little bit closer there. So now you can see this delta, and this is another big piece of evidence that tells us that there was once liquid water on Mars, because you don't get river deltas forming unless you get water flowing, right? And so this was a very important line of evidence to tell us, yes, at one time there was liquid water flowing on Mars. And this is a closer up image of it, and then comparing it to what a delta looks like here on Earth in Canada. All right, and so one of the things I want to emphasize with this slide is if you study minerals here on Earth, those are the same minerals that are on other rocky planets, for example, on Mars. So those two images on the left are showing the Martian surface, and what we see is that on the bottom, those similar pink and bluish colors, that is the same type of colors that we get on Earth for minerals on Earth. And so these are fake colors. These are colors that I told the computer to assign certain minerals colors so I could see them stand out a little bit more. But the picture on Earth that's on the right, that is from Long Valley Caldera, and Kayla showed pictures of those earlier, which erupted around 800,000 years ago. But you can see there's similar mineralogies on Earth in this volcanic ash deposit. So when I see minerals like this on Mars, I start thinking, oh, maybe that's an ash deposit as well. So that's a lot of the work that I do, is looking for ash on Mars and specifically looking for those types of minerals that we see. And then someone said Venus is another planet that has a lot of volcanoes on it. It's covered in a cloud, a thick cloud, so we can't see it very well with radar image, or we can't see it very well without radar imagery. The radar can go through and show us what the surface looks like, which is the image on the right. And there are a lot of different weird types of volcanoes on Venus as well, like types of volcanoes that we don't have here. And then Europa Clipper is another mission that I'm working on right now, and that is to look for habitable environments on other places other than Earth. And because it is an ocean world, it has a lot of water, so we'll see what we find there. We got the Europa Clipper mission, and it's on its way there right now. And that is what the spacecraft looks like, just to give you an idea of all the different components of it. It's a lot of engineering, but it's a cool spacecraft, and when it gets there, it's going to give us really good science. So this is more analog work that I'm doing. This was in a place in Alaska, the Valley of 10,000 Smokes, a big eruption there. Happened from this Nova Erupta dome in 1912, and you can see it blanketed the whole valley with ash. And so I was studying there, and this is a place I went with Kayla. And again, you can see the different colors, so that tells us there's different compositions of mineralogy there. And let's see, just more examples of the type of material that I collect here on Earth to compare to the minerals that we see on Mars. And this is my last slide. Sorry for going a little long, but I just want to leave you with some words to be passionate about what you do, be resilient, surround yourself with people who are supportive of you, and you're going to do just great. Just keep going.
Thank you. Thank you so much. Dr. Alexandra Matej Novak, would you say just one more time, are any of those volcanoes on Mars still active?
Not that we can tell.
Thank you. All right, so do we have questions for Alexandra? Dr. Alexandra, please go ahead, and we can line up again in person, any of the kids here, and anybody online. You are welcome to enter your questions in the chat or raise your hand and we'll unmute you.
Hi, my name is Isabella, and I was wondering what or who made you to start liking volcanoes?
Oh, so I knew I always wanted to have a job outdoors. And then I saw this movie when I was in high school called Dante's Peak. I don't know if you all remember that movie. And I was like, oh yeah, that's what I want to do. But one thing that really appealed to me about that was one, working in with teams of people. Like everybody had a different piece of the puzzle, a different part of the volcano that they were monitoring, and then all together it would give them a good idea. And then I also like that they were helping people. So when I first got into volcanology, it was to study it as a hazard to help people around the world avoid volcanism and the hazards that can come from it.
Thank you.
My name is Annabelle, and I want to know what inspired you to work for NASA?
I didn't have plans to work for NASA. I really just wanted to study volcanoes. And then just the way that things happen, you know, I looked for different opportunities when I needed a job, and one of them was studying volcanoes with NASA. So I was like, okay, I never thought I was going to be studying volcanoes on other planets, but as I was saying, once you learn how these things work on Earth, it's very easy to apply it to other rocky planets.
Thank you.
We have another question online from the Boys and Girls Club of Hudson County. Since there used to be water on Mars, could there be evidence of life there too?
So that is currently what the Perseverance rover is looking for. So theoretically, yes, if life had existed on Mars, there would be evidence. We have yet to find that. We've looked very hard. Doesn't mean it's not there, but we have so far not found any. And we're looking in a river delta, which seems like you would find, you know, if it was there, it might be there, but we haven't found anything yet, so.
Thank you.
My name is Brooke, and I have a question about so if like I have a question. What would happen? So like if you put an object if you put an object on Mars and the object was a metal on the surface of Mars, what will happen? Because
Well, I will go based off of what is happening on Mars right now. It's red because it's rusty, right? So there's a lot of iron on Mars, and it's kind of rusted. So I think if it was a piece of metal that was iron, it would get rusty, just like it on Earth.
oh, thank you for answering my
You're
question.
welcome.
Hi, my name's Marley, and what do you mean by 10,000 smokes?
Oh, good question. So we call it the Valley of 10,000 Smokes because when that really, when the volcano erupted, it erupted from this nova erupted dome, and it deposited all this ash. It was still full of a lot of gas and heat, and so all these little like fumaroles, like these places where the gas was escaping, was coming up through the deposit. So it looked like a bunch of little smoke holes coming up. So that's why they call it the Valley of 10,000 Smokes. Doesn't look like that anymore, but when the volcano first erupted, that's what it looked like.
Thank you.
You're welcome.
So, what was your favorite experience so far?
Oh man, well, I really like doing field work. I think probably going to Alaska and studying this area out here. It was really rough terrain, and it was very mentally and physically demanding, but there was really cool geology there. So it was a lot of fun to do. So.
We have one more question online. What causes volcanoes to stop completely? Why would they stop?
So volcanoes are fed by magma chambers. And so for a volcano to stop completely would mean the magma chamber emptied out and it did not refill. Sometimes they refill and sometimes they don't. It's just, depends on the geology there. But if the magma chamber empties out, there's nothing to power the volcano anymore.
Thank you so much. Everyone, thank you to Dr. Alexandra Mateja-Novak. And our next speaker, Alexandra, can you stop sharing your slides when you get a second? Dr. Edgar Rivera Valentin will be talking next.
Okay, cool. So, hi everyone, saludos. I'm Edgar Rivera Valentin, but I go by Ed. And this presentation is called Radar is Awesome. Alexandra used the word radar for Venus, and I'm going to talk to you about what that actually is. But before, let me tell you a little bit about myself, who I am, where I come from. So I was born in Arecibo, Puerto Rico. Puerto Rico is an island in the Caribbean, just south of Florida. Why is Arecibo important? Because Arecibo used to have the world's largest radar telescope. And so I do radar because radar was right in my backyard. Besides doing science here, I also have a life outside of work. That's my dog. His name's Bear. His paws when he was born were so big that it looked like a bear paw, so his name is Bear. I'm part of several teams, and I like to work with a lot of people and get to help organize people. So hashtag Team Radar is a group of folks who use telescopes on Earth with radars to study asteroids. Boricua Planeteers is a group myself and others made to help socialize those from Puerto Rico that are doing planetary science. And Planetary Scientists of Color is another group that we meet up at LPSC, Lunar and Planetary Science Conference. So scientists sometimes meet up at conferences. That way we could share the science we're doing and learn from each other to improve what we're doing. Random facts about me, I love musicals. Who here went to see Wicked Part 2? Yes! That was great, thank you. Wicked Part 1, Wicked Part 2, Wicked is like my favorite musical. Went to see it in Broadway, went to see it at different theaters, like I was just Wicked. That's it, that's the talk, Wicked. No, okay, so what drives me? So this is a picture of my abuela, my grandmother, and this is a picture of that big telescope I told you about in Puerto Rico. What drives me is, when I was a kid, and my grandmother would tell me, no hay nada que no puedes hacer, solo cosas que no quieres hacer. There is nothing you can't do, only things you don't want to do. Grandma? Yes. So Grandma was just letting me know, if you find your passion, if you find what you love to do, there's nothing gonna hold you back. You can pursue what you love, as long as you love it. And the other part of this was my grandmother, who was the matriarch of my family, was basically saying, I believe in you. And those are big words. So I'm going to tell you all, I believe in you, because getting to hear that from somebody, at least when I was a kid, helped me know that I can do this. So understand that all the adults here are here because we believe in you. We know you can do whatever you set your mind to. So this is what drives me, my abuela. And so that sent me off to do a bunch of different degrees. So I went off to a small college in New York where I got my bachelor's in physics and math. So that's my papi and my mommy, father and mom. I kind of had a similar road as the folks you've heard here. I started off with physics, and then like if you're doing a physics in college, you have to take enough math that like might as well also study math because you're taking so much math. But while I was doing that, I got to take this really cool class called planetary geology. And I was like, what? I could like apply this and study the planets in the solar system? This is really cool. So my college at that time, it's a small college, so it didn't have like a program in planetary science. So I made one up. And I talked to the professors and they made it happen. Why? Because I was passionate about it and I made it happen. Exhibit A, just like tell people it's gonna happen until it happens. Then I went off and got my PhD, so that's the doctorate in planetary science over at University of Arkansas. So that's from that side to this side, right to left. My abuelo, grandfather, abuela that you saw on the other slide. Then me, I was young. Back in the good old days, I was young. And then that's my other abuela, and then that's my sister. And then I also did, so Christine is from the LPI, I got to do an internship there. So that's all like part of why I went into the direction that I went to, planetary science, applying what I know from physics and math. And then what do I actually do for research? So earlier today, I used the word during lunch, planetary defense. And what does that mean? So planetary defense is, we know, from the pictures you saw, there's a bunch of holes on the moon. there's a bunch of holes on icy moons. Those holes are called craters. They happen when a large object comes in and smacks the surface. It makes that big hole. So that's called an impact. And we know they happen. And if they happen now, like that would hurt us, right? So I said, well, not I, but a bunch of people said, well, let's actually prepare and protect ourselves from it. So NASA has the Planetary Defense Coordination Office. Their job is to coordinate a bunch of different parts of scientists and people in lawmaking and stuff like that, and engineers. And so it starts off with, well, if something's gonna hit the Earth, you need to find what that something is. So search for asteroids, track them, make sure we know where they are constantly. And then there's characterize. Okay, you found the asteroid, so what? How big is it? How fast is it moving? What is it made of? Is it a big chunk of metal, or is it a big chunk of rock, or is it icy? Then you assess. Is this even dangerous to us, or is it too small and we don't care if it comes by? Or, yeah, it's big, but it's never coming by us, at least in a million years, so we don't care about it. That's assess. But let's say we assessed and we found something. So then it's plan and coordinate. That then gets different parts of lawmakers together to figure out what we need to do. And then mitigate, actually do something about it. Because we can actually push the asteroid away. Upstairs, I showed you DART, the Double Asteroid Redirection Test Mission, that spacecraft. And remember I said, that spacecraft, we showed that if we slam it into an asteroid, we could push it away. So we demonstrated we have the technology to protect us. Now what I do in my research is I do that last corner there, characterize. And for that, I use radars. So when you're doing astronomy, you typically go outside with like binoculars or a telescope, right? And you point it up into the sky and you're hopeful that some light from some star or planet really far away, that light finds its way to your telescope, goes through all the lenses, hits your eye, and then your brain goes, ooh, that's bright, right? In radar, we're impatient. We're not gonna wait for the universe to send us light. We send light out into space. The type of light we send is not the type of light you can see. It's different light, but it's still light. So we take that light and we bounce it off of the dish you see here. So follow the blue lines, bounce it off the dish, go up and hit the, oh, maybe it's the red line. Go up and hit the asteroid. In this example, the light comes back, we collect it, and we get a picture. Here's one picture of what that asteroid looks like. This is asteroid 2015 TB145. Asteroids have weird names. Actually, there's one named after me, so I guess they all do have weird names. But if you stare at this image long enough, you're gonna see it looks like a skull. Actually, it looks way better in the back TV right over there. It looks like a skull, and that was awesome because we observed it the night before Halloween, and I was like, excuse me? There's a skull floating in space? But just like when you have a flashlight, if you flash it over and there's something big, it casts a shadow behind it. In the other image where you see the asteroid moving and rotating, you can see that actually some of those shadows are moving. So those things that look like eye sockets, those are just shadows cast by a big rock. But with this type of telescope, a radar where we're sending light out into space to take a picture, we can take pictures of a bunch of different asteroids and planets. But why we do this for asteroids is because typically when you look at an asteroid through a telescope, you see that little tiny red dot. That's boring. I don't want no dot. I want the cool picture, right? So we take the cool picture of the asteroid, and then we can figure out, hey, are you a sphere, a nice little ball shape? Some of them are. Some of them look like what we call a regular shape, but if that TV is way better than up here. So some of them look weirdly irregular, and actually I call this one the alien head because you kind of see the two dark circles on either side, then the mouth in the middle, and it's going, ah! I like that one. Some of them have moons. So you see that little bright dot that's moving as the asteroid's rotating? That's a moon of that asteroid. And for some asteroids, the moon and the other asteroid are about the same size, and they over time hit each other. And so we call that a contact binary, and that's this one. And you see kind of how when it's rotating, you actually see that there's two pieces with a neck in between because they got connected. And then, so upstairs, I told you we have the technology to actually move this away. This is a movie. This isn't real. It's a nice little computer type of a movie. But it shows you what we did to that asteroid. We took that spacecraft you saw upstairs and we slammed it into this. The way the type of mission that we send, though, is going to depend on things like, is it a contact binary, or is it a sphere, or how big is it? If it's too big, we need to send something bigger. If it's too small, then maybe we can just like tickle it. But it all depends on this characterizing. So I do the characterizing part. So if we find something that's dangerous, the engineers can then make another dart and slam into it and protect us. And that is planetary defense, and why you should be a planetary defender. The end.
Okay, so time for questions for Dr. Edgar Rivera Valentin. Who has questions online again? Please feel free to enter them in the chat or let us know if you would like us to unmute you. Those of you in the room, anybody in the room with questions, come on down and let us know.
Hi. Just looking at this last video that you showed, I know you said it obviously is not real, but usually, like, how big are those devices that are pushing or like tickling them, like you said, in comparison to the asteroids? Because I was surprised at how small it looked upon impact there.
Yeah, so I won't get into equations, but energy is what matters, right? And energy is how big I am versus how fast I'm moving. So I could be something really small but traveling really fast and have the same energy of something that's really heavy but traveling slow. And in this case, we sent something that's small but traveling super, super fast and was able to give it enough energy to push it away.
So, when you're talking about, what happened when you're talking about stuff that happened in your college, what was it about? Like when you made up the idea about,
Yeah, so when you go to college, you get to pick the type of thing you're going to study, like physics, math, geology, chemistry. But my college didn't have a program for planetary science. And so I talked to the professors to make one up. That way I could also study planetary science.
Thank you for answering my question.
Thank you for asking it.
So, what equipment do you most like about like that they launch in space? So, what like equipment do you like about them?
Radar. Radar's awesome.
Okay.
Radar's the best equipment ever. True story.
Are big asteroids able to form craters if something small hits it?
Oh yeah, yeah. So in this movie, although it's a movie and it's made up, it's still informed by things that we know. And you see, yeah, you can see my cursor. This kind of circle there, that's supposed to represent a crater on the asteroid. And a lot of that, actually, all of the asteroids we've visited, we can see craters on its surface. And some of the radar pictures that we have, we also see the craters. So smaller asteroids can combine, still hit it, and give you that.
Thank you.
Mm-hmm.
What inspires you to be like this?
That's a great question. This. So this big telescope that you see here, this dish, this was in the city where I was born. And when I was about 3 or 4, my family took me up there to get to see it. And when I was walking around and they were telling us all the cool science that can be done with this, and the fact that it was basically in my backyard, got me thinking, cool, I can look up into space and think about what's happening out there. And I kind of made it a goal, since my abuela told me I could do whatever I want, I made it my goal to eventually one day get to go back and work there. And I actually got to work at the observatory for many years before coming up to work here.
Thank you.
Thanks.
I just want to ask, how do asteroids even come to Earth?
So asteroids, a lot of the asteroids, they kind of go around the sun, but between Mars and Jupiter. That's what we call the asteroid belt. But every now and then, some of them end up getting pushed inside, so between Mars and Earth. And so those end up every now and then having just the right motion around the sun, that as they're doing this, going around it, and the planet is here, it's doing this, and they both meet suddenly at the same point in time and space, and they smack into each other. Yeah.
Hi, my name's Anthony, and I was curious about, every now and then we hear on the news about sighting of an asteroid or something that could have a possible projection that we could probably see in the solar system towards us. How many times have we had to use this technology of hitting something, an object, and moving it?
0. So to date, so we hit the asteroid Dimorphos, the moon of Didymos, as a test to show, yes, the technology works. But we've never had to use this technology yet to defend us. To date, there is no known asteroid that actually poses a danger to Earth. We are fine. There's going to be an asteroid that comes by really, really close in 2029, April 13th, on Friday, April 13th, actually, which is a horrible thing. But it actually comes really close to the point where people will be able to go outside with binoculars and see it, because it's going to be close enough that satellites that are in space, it's going to fly by it. But even that comes by and keeps going, and it won't come back. There is an asteroid that was recently found that after we were able to get enough data on it, we found that it's not going to hit us, but it might hit the moon. It's a really small chance, though. And if it hits the moon, I'm pro hitting the moon. That would be fun to look at. But to us, we're safe.
Thank you.
What other items do you shoot to move the asteroids?
Ooh, there are a bunch of different ways that we've thought up to move an asteroid. So one of them, you smack it. The other one of the early ideas is you actually went up and you spray painted it. Because if you change the color of the asteroid, the way sunlight bounces off of it changes. And sunlight is basically like a little thruster. So you just add a little thruster, and that ends up changing the orbit of the object so it misses you. Another one is called a gravity tractor. Everything that has mass, like me, I weigh a lot, I have gravity. And everything that has gravity pushes and pulls on other things, So if I take a spacecraft, I don't have like ooh. If I have a spacecraft, or I have an asteroid and I have a spacecraft, and I take it and I park it next to it, the gravity of it is tugging it. And over time, that little tug adds up so that this avoids us. So those are just 3 examples of things that, technology that we have that we could use to make this weirdly shaped asteroid not hit us.
Thank you.
Yeah.
What is your favorite thing about your job?
What is my favorite thing about my job? I like being wrong, because that's the best point to be able to question how the world and the universe works, and then eventually having that eureka moment where you're like, oh, that's the answer. This is how things work. And that process of like being wrong, going all the way up to, oh, this is how this works, is super fun.
Thank you.
How are asteroids made?
How are asteroids made? How are they not made? So asteroids, we keep saying they're leftovers of the formation of the planets. So Linnaeus showed a planetary nebula, a bunch of dust all over the place, and eventually that dust comes together and make planets. If they're big enough. Some of the dust comes together and stays really small. Those are the asteroids. Sometimes a big planet can get broken into little tiny pieces, and it can also just then, those pieces become asteroids. Sometimes one of those pieces can hit the moon, launch pieces off into space, and those pieces become, you guessed it, asteroids. Asteroids are just tiny chunks floating out in space that are leftovers from things.
Thank you for answering my question.
Thank you for asking it.
I was wondering if you knew how the telescope was built.
This? Oh, of course I did. This is my place. So this started actually, so if I said the word chicken wire, do you know what that is? So when it was first made, they actually took that chicken wire and placed it. So first of all, this is huge. It's 305 meters across. So if you're going to build something this big, it's easier to build it in a hole. That way you don't have to dig out a hole. So they found a hole in Puerto Rico that was about the same size that they wanted the dish. And then they took that chicken mesh and put it on there and then tested to see if the idea worked. Once they found out, yeah, this is all working cool and cuddly, let's do this better, they took these panels of metal and started putting it. So although this looks like a solid structure, it's not. It's these panels about yay big that are placed onto the chicken mesh that then holds all those panels together so it forms a nice dish. The first part took about 3 years to build, and actually my grandfather helped build it. So he was a trucker, so he would move supplies from San Juan, which is the port in Puerto Rico, and drive that up to the observatory. Actually, okay, so another side story. So I was taking my family up to the observatory on the tour, since I was working there. And in part of the control room where we controlled this, we have pictures of how the observatory got built. And one of them was my grandfather's truck. And he stopped by and he was like, "It's my truck. Y'all took a picture of my truck." So I thought it was really cool. So whenever I took people up to the observatory to give tours, I'd be like, "That's my abuelo's truck." So yeah, so he helped build part of it. The first part took about 3 years. The next part took about 5 years. And then originally, this thing up here, this platform, used to be just one long line, which is you see here. This took about 10 years to build, and that was in like 1990. So it was in phases and chunks. And over time, it just kept getting better and better until sadly, back in the end of 2020, this entire thing snapped off the cables that are holding onto it and crashed. So now we don't have a telescope.
Thank you.
Mm-hmm.
What is your least favorite thing about your job?
Paperwork. So much bureaucracy and paperwork. Seriously, it's all the paperwork. Yeah.
Let's everybody thank Dr. Edgar Rivera Valentin. And thank you all so much for joining us for this. We're going to go ahead and call it a night. We really appreciate everyone's time. I'm going to stop the recording now. And